anfitrión, compañeros, compañeras y público en general que hoy nos acompañan. Mi nombre es Arely Fernanda Sánchez Gudiño, actual tesorera del Capítulo Estudiantil. Sean bienvenidos a la videoconferencia del día de hoy, organizada por el Capítulo Estudiantil Material Advantage y el Departamento de Ingeniería Metalúrgica. El ponente es el doctor Alisson Duarte, de quien me permitiré leer una breve semblanza. El doctor Alisson Duarte es profesor en el Departamento de Ingeniería de Materiales en la Universidad Federal de Minas Gerais, en Brasil, y es el cofundador de SIXPRO Virtual and Practical Process. Tiene un postdoctorado en metalurgia y es especialista en simulación computacional de conformado y tratamientos térmicos. Su experiencia profesional incluye realizar simulaciones de procesos de conformado y tratamientos térmicos en el Centro de Conformado de Precisión en Columbus, Ohio, Estados Unidos. También controlar procesos de laminado en ArcelorMittal, actualmente Happyram, e impartir clases de ingeniería en el Departamento de Ingeniería de Materiales en el Centro Federal de Educación Tecnológica en Brasil y en los departamentos de Ingeniería Mecánica e Ingeniería Metalúrgica en la Pontificia Universidad Católica de Río de Janeiro, en Brasil. La conferencia será impartida en inglés. Si lo prefieren, pueden hacer sus preguntas en español o bien en inglés. Démosle una cordial bienvenida al doctor Alisson Duarte, quien nos presentará la conferencia Modelado matemático y simulación computacional de procesos de forja. Good afternoon, Dr. Alisson. We are much obliged for your time, and I yield the floor to you.
All right. Thank you for the introduction. Very nice. And I would like to thank first to Professor Dr. Bernardo Morales for the invitation, and also for all the team that is here setting this webinar. It's my pleasure to be here and have this opportunity to talk to you. All right, can I start? Okay. Are you? If you have any problem or connection or to hear me or to watch to my screen, please let me know. But now, let me just make sure you can hear me, right? Is everything okay? Okay, thank you. All right, so my idea is to talk to you about the modeling of forging processes. If I have time, I will also talk about another processes like heat treatment or stamping and to say something about those processes. But so yeah, my name is Alisson Duarte. I'm a professor at the Materials Engineering Department and also work for SIXPRO. SIXPRO that is supporting us in this event by the use of Keyform as a FE model code for forging processes, for forming processes, and also heat treatment processes. All right. So a short presentation. SIXPRO today it started working in South America, actually in Brazil first, then South America. Now we for some time have already been working with companies and some universities in Mexico, and yeah, we also have some customers in US, also Portugal. So basically, what we do is that we work with some technologies. They are Keyform, Dante software. We also are a partner in US. Also JMAT Pro, that is simulation for materials, for metallic materials. ESI is for stamping. Fraunhofer Institute is in Germany, is also our partner. And also another one, very specific technologies, OmniCAD and Sorbit. So basically, those are our partners in a commercial way. That's it. And SIXPRO works here in training that provides training to the industry and also to the universities. Also do researching. We have plenty of papers, technical papers, academic papers that are focused on those ideas, on working on forging and forming simulation and used right in the industry. I would say that our program today, our webinar, is in the middle of the training, researching, because we talk about that. We also provide software to the industry and to the universities, and also do consultancy when it's needed from our customers. Well, and the main processes we work with are stamping, hot stamping, heat treatment, hot forging, warm forging, cold forging, materials, ring rolling, longitudinal rolling, profiles, plates, flat, and also extrusion. When we say extrusion, sometimes we have steel extrusion. We put that in hot forging. But when we talk about, light alloys like aluminum, magnesium, and long profiles, then the extrusion has specific features that are needed. So that's why we make this difference between hot forging and extrusion as well. I would say extrusion of light alloys. All right. Okay. So that was a very short and initial introduction about 6 Pro that's providing us this possibility here. Let's talk about modeling. I'm considering that we have students that maybe have never used FE model or have never actually worked on a project for that. So I would say that what we do is we use those, we divide our geometries of interest. Let's say this is an initial geometry. We can call this a preform, that is going to be forged in order to get a crankshaft. I will show this video here, as you can see, how the part forms during a forging operation. I hide the upper die. The top die is not here, but it's here, but it's not shown. And you're going to see the part being formed on the bottom die, as you can see there. So it's interesting that in this case, as you see here, the part forged is this here. This is all the parts forged, okay? And we have this shaft on it. And as you can see, in these parts, these areas, we have bigger elements, and this area here is a very thin area, have smaller elements over here, right? So what we have in Keyform is not a remeshing, no. It's a technology we call adaptive meshing, because the mesh is adaptive depending on the need, depending on the geometry, curvature, on the strain distribution, temperature distribution. So we have this adaptive meshing. And here is an example of open die or closed die forging operation. All right, so that's what we're talking about. So I will show this video one more time. All right. Okay, in order to do this, we need a few information. First, we need data. We need data for the material, and also I need the CADs for the initial billet, the dies, also the material like flow stresses, thermal conductivity, specific rate, and others. Once I have those data, so I need to set up the simulation. So positioning is important. Which type of equipment, let's say a press or a hammer, which are my process parameters, temperatures, furnace, which type of friction, heating, and other boundary conditions that are possible to include in the setup. Then the software works on it, okay? Then you have this processing. After processing, then you can analyze geometry, defects, temperature, stresses, strain, loads, or you can analyze the dies. I'm going to show you a few examples here Pretty much, it's pretty nice. And also, this is a simple way. When you do a setup, you process and you understand what's happening in the processes. But in software, we can also optimize parameters. We can optimize the manual setup of the simulation. So we are really working further here. We have, for example, API, and API is when you can actually put your software, Keyform, in contact with other softwares. We can also think about put in contact with your presses, with your equipment. So you have this interaction in between the simulator, Keyform, and also equipments and other softwares. It's very nice. Sometimes you can even run a simulation without even open Keyform. So you do everything from your applications, other applications. It's very interesting, and it's really developed. All right, I know it's too much theoretical, or it's too much theory right now, but let's go further so we will understand that. Temperature and strain rate, of course, here's an example of the importance of having a good material data, because of course, if you get a material like 800 or 1100 Celsius degree, of course, the material at 1100, it's easier to be formed. The material at 800, it's more hard, it's harder. So it happens. So you need to have information for the material, like for different temperatures. Also, you need to understand that for each temperature, let's say for 1100 Celsius, for the same temperature, the material can behave differently depending on the press speed, depending on how fast your process is. If you do a process very slow, let's say I do a very slow process of velocity, for deforming my material at 0.4 strain, I would need around 40 megapascal, right? So that's what I would need. However, if I go it fast in the forging process, the same material at the same temperature, I would need a lot more, stress. It means I have to do a lot more force in the press. Also, the dies, they suffer much more because I do much more stress in the dies. It means you can break them, the dies, and these questions are answered when you actually simulate the process here. So you work with different temperature, different strain rates, and that's very important. And you understand the reflection or the results in the part, defects, presses, and also the dies. It's really important. Okay, so you have this idea of the importance of the press speed. Let's get here. This is a hydraulic press. This hydraulic press, let's say, is going to be very slow, and it's a customer of us. They do those open die forging. So there's a huge bar here, and let's see. I think it's enough. So we're going to see that it goes upsetting this big bar slowly. Then you have this mechanical, this is a friction press, and you can see 1, So it's interesting. Here you have two blows at the same with the same die. It's faster than this process here, this hydraulic press on the left, and in the center have this friction press, and you do two blows. It's faster. Now here we have a hammer. So the strain, the deformation of the parts, it's really, really faster. And all those parts are at the same temperature, probably at 1200 Celsius. However, here it behaves different. Here behaves different. Let's see how fast a hammer can be. Well, yeah, I did those videos myself, recorded that myself, how from our customers, they allowed us to show it. And we have already, simulate all of those processes. And it's really important to take into account the material behavior in different speeds, in the different strain rates. All right. Okay. So how to have those material data? Most for the forging, the most common way is to get, for example, the compression tests. Compression tests, you can see here 5 specimens, and they were all compressed. And from those, we get material. That's one possibility. Another possibility is to get their softwares that they already simulate the behavior of the material that we need. For example, this is JMath Pro. So from JMath Pro, I can input the chemical composition and provide the field information more, and then I can export, for example, to key form. It's possible. So you have tests, have simulation, and here I'm not talking about simulating the process yet. I'm still talking about the material, because material data is important. In key form presents us a very large amount of material is already there in the library. So, but here it's important to say this. And we need to, this is only the flow stress. So I need this for different temperatures, okay? From 20 to, let's say, 1300 Celsius. And also for each temperature, I need, let's say, at least 6 speeds to have a wide range of behavior for that material. So material is really important, of course. And here, from these, we got, for example, there's behaviors, the flow stress data. So you have this experimental, and then from the experimental, you get this complete curve in order to simulate. Then we simulated that, and you could see that in experimental, we had like around 400 kilonewtons press experimental. While simulating this, we got pretty close. It's a real case, and it was very important to define before doing the experimental. We define the company. This is one of our customers as well. If you want to see the paper, it's unfortunately it's in Portuguese, but if you can see the paper, it's there. By the way, I'll provide you the PDF at the end of this presentation, so you'll be able to get this presentation and also all the information inside the presentation, such as links and videos that I'm going to show it to you. Before going into the predecir, we simulated and we found the necessary load for the process. And when we went to the predecir, we saw that the predecir was in accordance to this to simulation. All right. Also, it was a cold forging, so it's really important. The question, the matter of the dyes, because the dyes are very, they suffer too much, many stresses. So we also have to check at least the effective stresses in the dye. So you can see here, so the dye is assembled by 3 dyes. So 3 dyes makes the tooling. And also this company, they have others dyes here. They are feet, shrink feet, other dyes here. So they can decrease the tensile stresses in the dyes, which is very important, and also decrease effective stress. So it's not shown here because it's a matter of confidentiality. However, you have effective stress here. And also another important thing to see is to check the mean stress, because the mean stress says if we are too much tensile or if we are in a compressive. So the idea is to get compressive stresses other than tensile stresses, because they can break the dyes. It's very superficial here what I'm talking about, but we have much more than you can take a look into the dyes and analyze those dyes. You can even define the number of blows, the number of parts until the dyes fail or would break in a fatigue, okay, by fatigue. So there are too many possibilities. Okay, here, as I said, it was about to say the modeling. It's a general idea. Now that I gave you the general idea, I'm going to show a few examples of what we can do with, okay, so forging. I'm going to fix on forging. The first idea is we can conduct open die forging operations. As you can see here in the top, I have this what we call manipulator, and it handles a big bar, and this bar is then pressed by dies, all right? And for simulating this, I can consider, you can see here, I can consider this geometrical manipulator, or to make it easier and faster, I can also use this graphic manipulator. So the manipulator, it moves the part and it rotates also the part, so it makes it easier if I want to simulate this process. So this is an example of open die forging. I was saying graphic manipulator, so you have for general analysis, automatization of the simulation, make it faster. Also geometric manipulator, you make positioning, sometimes it influences on the shape of the forging or the part being forged. And so you can check positioning, heat exchanging. Of course, you can check how part loses heat to the dies, how dies can deflect during the forging process. You can check these and much more. All right, I already showed to you this closed die forging for you to have an idea. This is also cold forging. As you can see, cold forging is very, very tricky, and we need to consider a lot of dies. You can see every die has a correlation to the other. Sometimes it's fits, sometimes there is a distance between dies. Sometimes there is nothing, it's just there. So it's important, as you can see, just to do this very simple part here, a lot of tooling, a lot of tools we need to do this. I'm going to show this here. This is the final forge blow, and you can see here it's forging there. All right, then the final forging blow, it finishes the part. Over here, you can see the punch, how the punch deflects. Of course, it's pressing, there's a load and punching the part, and you can see that this punch, it dislocate or goes more than 1 millimeters up. Also, there is in the diameter, there's an increase in the diameter. It might be a problem or not. I have a deflection here because those dies suffer elastic deformation, elastic strain, and also it might get plastic strain, which is not desirable, which we don't want plastic strain, but it might happen, and that's a problem because it's going to lead to fatigue very soon. So it's a problem. You can check all of it in the software. All right. Another type of operation, electric offsetting, is when you have here one electrical contact, and there is an electrical current passing through the part, so the part gets heated, and you do this forging by electrical offsetting. It's interesting. It's a possibility. Maybe a few people know it, but it's interesting. Also, I put here forming. You can also, I'm talking about forging, but you can also work with sheet metal forming. As you can see here, this part is going to be, forged or stamped in order to get this truck part. You can see there, and you can actually design a much more precise part or a much more precise process. We do that every time to many companies, and it's pretty interesting. It's challenging, but it's when you do that, it's very nice when you see the part there working on a truck or working on a car, working on a equipment. And the equipment is very nice. Grain flow. When I see talking about this fiber flow, you can also, it's also important for the forging. You can see this part here. You're going to see there is this fiber flow, and of course in the software you should take a look in that to understand if the part has an acceptable flow, metal flow. That's really important. There is also here, I'm not showing this here, but there's also a defect here that we also can check it and predict it very well. All right. So there are other needs in the forge operation, like how the metal flows, because that's really important. During the use of this part, it suffer loads, and those loads should be in accord to those fiber flow, right? I'm not sure if everybody knows it or already studied that, but just mention this. Underfilling, of course, if you have a process that you have a metal and the metal doesn't fill your dies perfectly, you have a problem. For example, my part was designed to be here, also down here, also all up there. So there is this underfilling. It's a problem. So I have to work on this part in order to actually get the fulfilled part, and then I get the right final forged part. This is unacceptable, so it's a scrap, and you lose money, you lose time, and so on. This is a 2D to make it easy to understand. You have also a way to check this by 3D, 3D simulations. It's very interesting, very nice. Okay, and all right, there's this together, underfilling and lapse. Lapse is when you have the material that goes against its material. Like you can see, let's say here, this part is coming to this part, so you have this we call lapse or folds, and so you have underfilling, and some small laps here. It's a problem because a lap is like a crack. So it concentrates stresses. And when you use that part, it's going to break there because a lap, so it's this is, as I said, concentrate stresses. It's a problem. And we have to avoid laps. Well, other analyses like surface flow analysis, you can see here problems here. And in a simulation, you can check by color. It's very easy to understand, to see it. You don't need to understand the actual finite element. You just need to actually understand the process. Nobody, if you don't have skills by using softwares and codes, you don't need it because the software is already set to provide you easily all the results you need. So that's it here. For example, you can check also cracks. It's different from folds. Folds or laps is when the material goes against itself. But in this case, there is actually a crack. So this material, it tries to come here. There is this tensile stresses, and actually you want to separate material. So here you have a crack. I said a fold is like a crack, but here you have a crack. And the most conventional way to check cracks when you is by using damage. You have a lot of damage criteria in key form. So as you can see here, it says that here there is a huge possibility of cracking, and when you go to the practice, you can see those cracks. In this case, for example, you have here a high damage, and when you go to the practice, you also see those cracks there. So it's another type of defect that you can check during the simulation. All right. I showed you a little bit about defects in forging, now about die analysis. For example, if I have, this is a die, it's a bottom die. You can see that I can check first of all the effective stress. You're gonna see that I have very big or high effective stresses here, that they are coincident to the parts to the areas in the die that will break. So the most important, the first very important result we have to check in the die is the effective stress, or are the effective stresses. Because if the effective stresses are too high, it means it's getting closer to the yield stress of the material of the die. So it's important that we analyze it, you know. Second, where, I didn't say that, but it's also mean stress is also important. So you understand if it's too positive or too negative, or too tensile or too compressive, it's important. Where, as you can see here, where predicted areas with where prediction, and when you go in the practice, you can see here very, very weird areas, you know. So it's important to analyze also where, because you need also to get to a point when you can like predict the amount of parts you can forge with that die, because if this tooling, because the tooling is very expensive. So it's important to have this dimension of how many blows or how many parts I can forge with this tooling. So it's economically, but money is really important. Also here, we can predict more directly when a die is going to break. For example, this is a project. It's a near net shape project, near net shape. Because when you want to get, like you want to forge closer to the final part, you know, to avoid any machining, to reduce the amount or the volume of material that you purchase to do that part. So you want to optimize the project. Here they tried to optimize this gear, but it was there was too many stresses, and it broke here. And in the simulation, you can see that right in that area, in the simulation, it says, all right, around, let's say, 250 cycles after that, the die is going to break. The die is going to suffer a fatigue failure by thermomechanical fatigue. And it's possible to measure or to have this dimension in the simulation, you know, like around an average amount of parts that I can forge before break. But this is very, very critical. And sometimes the companies go there and try it by trial and error. But you need to, you know, to conduct the simulation because those dies are very expensive. All right. Also, microstructure, you can check microstructure. I'm just going to show you an example here. I have this billet, then upsetting the preform and the forged part. And you can check the grain size, you know, because you have a scale. You can check the percentage of recrystallized material, you know. As you can see here, this is this micrography, and then you can check right there. You can check the same areas, and you can understand how the grain recrystallize, how the material recrystallizes, how the grain increases, and how much it increases or decreases. You know, that's very interesting to check in the simulation. I'm going to provide this to you. I know I'm talking about that very, very fast, but I'm going to provide this presentation to you and also some videos. I will also, make a comment about heat treatment. It's important how, for example, we can check to conduct quenching and tempering. There is here, this is a fork for aerospace industry. And here you can simulate the amount of martensite. Of course, here in those ads, you have much more martensite because it's much more fast, the cooling is much faster. And here, the cooling is lower, so you have lower amount of martensite, you know. And then you have this distribution of final properties like hardness, resistance, mechanical resistance. So you have all of these. In this case, we have this checking point here, and you could see a lot of martensite there. Well, we did also one trying because let's say, okay, you have a specification of hardness, okay, there, and it has this hardness, and you say, okay, I have my process here, very good. However, you can put the material, there's this range of chemical composition in the material, and that changes everything. That changes the curves of transformation curves. And for you to have an example, for the same alloy, if I get the same alloy in the bottom limit of that alloy and the upper limit of the same alloy, you see that at that point, I can get from 430 Vickers up to 600 Vickers, which is very wide, sometimes not acceptable, and sometimes you say, okay, I'm going to do this heat treatment and I'm going to make this work. But sometimes it's not in your hands. Sometimes the material, it provides you a very different, very different results because the material behaves differently. Well, it's important that we simulate this before because I have to also think about this. I have to design a more stable or robust process. I have to understand that the material can provide me this wide difference, and then I can change the way I do my process. So I can try to, to consider that variation of the material, and then to have a more stable result, like a more stable final process. So by simulating heat treatment, you can simulate a lot of different processes, also variate a lot of variables. So it's important as well, because most of the parts, forged parts, they are preheated, or then they are heat treated afterwards, and that's important. And now I'm going to talk about here. I'm in attention to the time. I think we are fine. We have like 35 minutes. It's fine. Industrial efficiency. It's important because I'm talking about examples or ideas. There are much more, of course, but it's important to show that it really makes sense. It really works in the industry, you know? It's not like, oh, very nice, or like a very colorful picture. That's nice to study. No, that's not the case. The case is that it really makes sense and makes difference to the industry, to reduce costs, increase profitability, to increase marketing share. So it's really important to have simulation. So I'm gonna get this process chain industry. It's very easy. Like I have the steel maker, then I have a forging company that purchases steel, and then it forges and goes to some companies that work on that, or that mounting, or So automaker or truck maker or whatever, and so we can simulate forging or forming everywhere. For example, the steel maker, many times they also rolls. So if they have a siderurgy, they roll their own steel before selling it. So you can roll it and sell bars to the forging. Or sometimes you sell rings to the forging. Or sometimes you sell very big bars and maybe heat treated, or probably heat treated, to the forging industry. So the steel maker before forging already uses steel form to provide a good part or good billets to the forging industry. All right. So in the forging industry, you have also, if you need, have open die forging, closed die forging, heat treatment, rings and rolling. So you can do whatever. It depends on each company. So, and also forging sells the parts to the other companies. And you have, for example, I showed you that fork when you have machining and a lot of heat treatment. And key form can be used in every part of this chain, industry chain. I'm going to focus only on the forging and customer of the forging, the systems. And for example, I'm getting some examples that I can show to you here. So here you can see the shaft is a gear shaft. It's big. So what they do is they forge it and then they heat treat it, right? And here you have the final microstructure. It's simulated and also heated by simulation. So here's the forging simulation. Here's the heat treatment simulation. And it's interesting because what they did is they used to do this part, like big part like this, without those teeth. And then now they are much closer to the final, so they use less material. And it's very important. I'm going to show a video to you in a couple of minutes. And then they were thinking about, well, do I really need to heat treat this part after forging? So they conducted in the simulation first, they controlled the cooling of the forging part, and they figured out that they could do an innovation, like they could sell the equipment, like I could say this, they were heat treating that before, but they found out that they could not conduct heat treatment anymore. So they decreased a lot the costs of the process, because they were much closer of the final process or the final part, and they didn't need to heat treat anymore. This was really nice. And it's interesting because their customer also used key form, but with different idea. You can see the forging was forging and heat treating, and okay, key form, how can I reduce costs? And then figure that out. All right. So their customers, you can see, this is the same part. Is this part here became this part here. So this customer used key form for analyzing residual stresses. So residual stresses were there, and they checked that. They could check the distribution of martensite, for example, the volume of martensite distribution. You can see much more martensite in the surface, of course. And if you have, if you're interested in checking this, there's the paper here. As I said, I will provide you the PDF of this presentation. Then you can click there and find the paper. All right. So it's very. My idea here is to show that it really makes sense using simulation. Okay, here is a very short video of the company. One of the company that I showed there is called, they are called Uniforja. And I'm gonna put, it's not in Spanish. I'm gonna put these subtitles in English here. It's very short, it's a 1.5 minutes. I'll show it to you here right now. All right, okay.
Bom dia, pessoal. Meu nome é Rodrigo.
Bom dia. Meu nome é Gustavo.
Nós somos da Uniforja. Projetos de forjados especiais, de acordo com a especificação do cliente. Vamos falar sobre 3 casos de estudo, né? Como pode ver nessa imagem aí no canto inferior direito. É uma pré-forma. É um eixo dentado, né? Diminui o tempo de desenvolvimento, né?
Uma próxima etapa, posterior à etapa de forjamento, que o Rodrigo bem falou, né, seria a etapa de verificar a necessidade de um recozimento. Então, a gente avaliou a temperatura de saída do forjamento. Então, a gente mapeou o quê? Através do Q-Form, a gente fez um mapeamento da taxa de resfriamento ao ar e também da taxa de resfriamento ao forno. E aí, seguindo nesse patamar isotérmico, o final da estrutura vai ser perlita. E para validar todo esse processo de simulação, nós fizemos um processo prático e verificamos sua microestrutura. Nós obtivemos o resultado satisfatório, como o Rodrigo bem mencionou, de redução de massa em torno de 15%. A gente reduziu o tempo de tryout, não fazendo por tentativa e erro. Também conseguimos a eliminação da etapa de tratamento térmico através desse resfriamento controlado. Então, a gente tem a agradecer à Uniforja, que nos permitiu a possibilidade de utilizar uma simulação como o Q-Form. Então, nossos agradecimentos aí a Six Pro pelo apoio e toda a parceria aí desenvolvida.
Of course, this is a short version of the speech.
De redução de massa em torno de 15%.
This is a short version, but you can also, at the end of the video, it shows the entire speech of them, the lecture is very nice. And but it's important that they reduced 15% of steel that they were purchasing. That's too much. They reduced a lot the time of tryout, like try to get a part out of to be sold, to sell it. Also, they eliminated the heat treatment, and also they decrease a lot the chance of accidents. That's really important in the industry. And also they reduce a lot the wear in the dies. You know, it's in English here. It's interesting if you have that. If you want to check that, then just go in the PDF and click here. Turn the English subtitles on, and that's it. All right. So this is one case. Okay. There's also another companies that they reduce, like examples, 14% steel cost reduction, die life increasing, operation reduction, the number of operations, they reduce it. workforce reduction, like less employees, less cost, and they can have a wide possibility of different geometries with the same process. It's all possible because of the simulation. You can see they were conducting this part, has this flash. This in red is a flash, is material that you waste material. And here, after doing simulation, they found out parts without flash and parts that goes direct in the equipment, and without anything. They only forged that, and that's it. You can see this on the right. The part initially, it had the flashes, also had to be drilled. Those holes were drilled, also machined. But after doing simulation, they got 24% cost reduction. And also now the part is all forged completely. There is no drilling, there is no cutting operation. It's only forged. Those holes are forged. And it's really important, or really interesting, those works here. You can see also from the point of view of the dies, here you see the die. This is the die was broken, entirely broken. You can see here is one part of the die and another part of the die, and what you see here is the part that was broke, or broken, and they could make it work. And also here you see another, like this is one die that's like 60, let's say $20,000, one die, and they broke it, so they had to, it's like you get a car and throw it in the garbage, like a car, and so you can work on that. First of all, checking effective stresses, understanding it, and then you have a more appropriate process with a more appropriate die. Because you have a lot of time, you have to purchase material, you have to machine it and heat treat, and then try it, and then it breaks. Then you have to do everything again. So it's much, much more efficient if you simulate all of this technology first, Or sometimes you have a problem in the line, and sometimes you want to increase, or like I said before, want to reduce costs for a process that already exists. So you can simulate in order to get better conditions, better processes. Here is also a short video. This guy here talk about the importance of analyzing the dies. I'm going to show this.
E a nossa empresa aqui, a empresa onde trabalhamos, a Minusa, ela está sediada na cidade de Lages. Esse item, denominado segmento da roda motriz, foi que surgiu a necessidade do nosso simulador. Nós tivemos inúmeras fraturas, setups perdidos, desconforto na linha de produção parada, e nós sempre buscamos respostas no tratamento térmico, no fornecedor de matéria-prima. Não que isso não possa acontecer, uma falha no tratamento térmico, uma falha no fornecimento de matéria-prima, mas nós encontramos realmente o que estávamos buscando como resposta depois da aquisição do simulador, onde vários de nossos projetos, não só esse dos segmentos, mas outros também, eles apresentaram uma tensão efetiva nas nossas matrizes acima do permitido para aquela matéria-prima na qual nós confeccionamos o nosso ferramental. Nós tivemos um ganho considerável na vida útil das facas de rebarbação, dos pulsões de furação e dos pulsões de forjamento. A vida útil desse pulsão era de 2.500 peças e tinha que ser retrabalhado com solda logo após esse número de peças de buchas forjadas. Hoje esse pulsão tem uma vida útil de 8.000 peças e ele só é retrabalhado com solda após 3 lotes, após o 3º ciclo. Nós praticamente eliminamos o setup intermediário, e com a utilização e com o auxílio do Keyform, né, do simulador, nós conseguimos sim aumentar muito a vida útil desses pulsões. Para eu que trabalho diretamente na produção, você poder mensurar, né, a quantidade de peças, quantificar a quantidade de peças, o número de peças que um ferramental pode produzir, é de extrema importância, né, para o desempenho, para a eficiência de cada linha de produção. Então, pessoal, eu queria agradecer a SIXPRO em nome do professor Alisson Duarte. Queria só complementar que quem trabalha na área de forjaria sabe da quantidade de variáveis que tem um processo de forjamento. Essa quantidade é imensa, né? O Keyform que nós utilizamos aqui, a probabilidade de sucesso é muito grande.
So it's also a short version of a 30 minutes lecture, and I got specific parts from the dye analysis. So the previous video was talking about forging defects, also talking about heat treatment was very important. I didn't talk about that, but they checked about material, controlling cooling rate, and forging problems. And this one is talking more about the dye analysis, which is tremendous important. And I'm almost finishing. Now, I would like to say that we have already provided to Professor Bernardo Morales, doctor, and the access to Keyform Cloud version. And I mean, I am the technical guy, so I have to say that people, the guys from Keyform, from SIXPRO, they are trying to help to provide this license for your university. And the idea is interesting because this cloud version, it's very nice because you can use in your computer, you can only install the software. And it's interesting because if you have a license, there is a license servers, they say, okay, you can simulate in your computer, right? So there is this middle server, they say, okay, you want me to simulate, so I'm gonna send to this server or to this server, or to maybe to this server. So those servers, they do the calculation. So imagine this. You can install Keyform in our computer, any computer you have, it doesn't matter. I mean, computers nowadays are very good, but who is gonna calculate your simulations, not your computer? So it means you don't need a very strong computer. So there is a server that can be here with us in SIXPRO, the server can be everywhere, can be even in their university. But your computer will work like you prepare your model, you ask the server, cloud server, to conduct simulation, and they give you back your results. It's like doing your computer, but much faster because you're doing in a server, in a cloud server. So basically, I know maybe it's a little bit confusing, but basically that's how a cloud version works. And finally, there is, here I'm just talking about forging simulation, but there is a very short training I gave to another university in Mexico. And the guy, there's some guys here, they put Spanish subtitles. I cannot say they are right, but I can say they can help. And as you can see here, predecir. I'm going to just one second here. You can see.
I'll ask you to send an email message
like
to
showing possibilities of how
and
under filling labs.
Actually,
and
maybe if
you'll be able to work by yourselves. It's like a short training. But Keyform, if you check this video, this complete video, you're gonna see that at the end you have Keyform. You have also like a tutorial that's very easy, like step-by-step tutorial. So anyone, any student doesn't need to know process, doesn't need to know materials. Any student can do a simulation. And finally, as I said, I'm gonna give you this PDF, And finally, I would like to mention this forging Olympiad. It's for undergrad students, okay? If you check in the key forms Olympiad there, you can go there and ask, any student can do that, ask to participate in the Olympiad. We had the 2016 edition, and now we had all those editions. If you come here, you're gonna see the reports of every winner. The three first winners is very nice, so you can, okay, just click here, participate in the key form Olympiad. We are very proud because we have been helping students to, to get prepared. For example, this is the 21 edition. So it's more than, like here, 19 countries. And I hope now it's going to be 20 with Mexico as well. And to get in this Olympiad. It doesn't matter the result, because when you are preparing to the Olympiad, you learn a lot. Because first of all, you start understanding how forging process works in the software. And then you take a look into those guys here reports, and you're gonna see how they thought, how should be a good report. And then you're gonna have like increase your networking with many other students, and also researchers, professors and doctors that are very focused on helping students everywhere. That's my case, helping students everywhere, working on forging simulation. So there is a lot of information in this PDF that I'm going to give to you. And this is the end. I would like to, again, to thank for your attention and to say that I am at your disposal. You can send me emails every time. And that's it. Let me provide you the PDF file in the chat. All right. PDF goes now in the chat. I believe everybody has access to it right now. All right. Thank you again.
Agradecemos mucho la tan interesante videoconferencia del doctor Duarte, y a continuación realizaremos la sesión de preguntas, por lo que les pido que quienes deseen hacer una pregunta lo pueden escribir en el chat o pueden alzar su mano y hacerla directamente, o también los que nos estén viendo por YouTube, ahí también pueden dejar las preguntas que quieran realizar.
América, voy a hacer una pregunta entonces. Alisson, when you talk about all these properties that you need to input into the model, we know that there are several different models to model the properties themselves. How easy is to input that into this software?
Oh, it's very easy. I mean, yeah, you can actually prepare that in an Excel file and import it. I don't know. I'm not sure if that's what you're asking for, but
yes.
Yeah, if you have a test, a compression test, for example, or any, let's say, heat exchange in function of temperature, just put in Excel and you can import it.
Okay, great. Thank you.
Anyway,
Carlos, tienes...
Sorry. Yeah.
Hi, Professor Alisson. I have a question. Can you tell us something about like which have been your most challenging design that you ever made?
Interesting. Most challenging design. I have to tell you this. There is I can tell you that I have been working with a lot of very complex parts, but there was one time that was a very simple part. It was like a tube, and I had to achieve a very, very round part. It's like, it was unbelievable because I had to produce that tube, and that tube is a very simple part, right? So, but I had to produce that tube in a very, very strict roundness. And that was not easy because, okay, we have customers that they do tubes like the management process, you know, you do like some sort of drilling and you produce those pipes, those long pipes. And those pipes, they are very tough. Let me show you this. If you don't mind, I'd like to share this here. Okay. 6 Pro. Oh, by the way, we have a lot of cases in our webpage. And papers and case for stamping is also in English. Whatever. I have to find this in English anyway. Forging, heat treatment. I have to tell you, if you talk about heat treatment, it's a lot more tricky. That is really challenging. But when you're talking about shapes, those parts here, find this. All right. This is a paper we wrote and with this company named management, VSB, Valorec Solution Tubular Management. And they had to produce, I'm talking about those type of tubes that are really long and they have many, many problems because they can be oval, they can be not linear. It's crazy. And after rolling that tubes, we have also to quench it. And it's completely crazy because it's a very long tube. So you have to, to send water in the middle and then, have to turn it. Well, so this is interesting. I'm talking about the most challenging work. But if I go and answer to your question direct, like shape, then I can talk about gears. Gears are the most challenging parts we have ever done. Also shafts. I have a lot of those and questions, examples, but only some of them, the companies, they accept to publish it. So let me show you one example. Well, I would most talk about you that there was one time I was in US working for a company named Invitan, and there was one gear very, very similar to this one. That was really tricky because it's not only a matter of shape, as you can see, we had to achieve the best condition. So to get very close, but you still have this possibility here, and then we have to work with the dies and do like assembling dies. And it's really important because I can, for example, okay, you see that is a complete die. And this die is only one part. And I can work in such a way that I can pre-divide this part and using like a divided tooling, I can do that in order to do not break it. So the possibilities for gears, in this case, they are very wide. So those parts, they are very challenging. It's not just a matter of simulation. Sometimes you have to worry about the, let's say, scale, about oxide, and that oxide. And that's also important to understand is And sometimes, I'm going for this, sorry for the long response. Sometimes the idea is to do not a hot forging, but also if you go to the warm forging, all right, if you do also warm forging, then and then you can see warm, you have all the type of problems, and the stresses in the dies are going to increase a lot more. But you're going to get a material that has a higher mechanical resistance. So I would say that every time that I get those gears, they are more challenging, not because of only the geometry, but because we want to get as near as possible to the final shape. I don't know if my question is okay for you, but that's it.
Thank you. Another question from Miguel. Has this technology ever been implemented in a real-time process in the industry? Do you see this technology being implemented in a real-time process in the near future?
Good question. Please just let me. Okay, I'll show to you this here. Second. Second, I'm open this presentation here. It's take a long time. No, already opened. When you ask me about real time, let me show you this. Is the idea. The idea is that this is key form, right? Okay, this on the right side, this is key form. Okay, this is key form. And you can see this part. Oh, you can see it's a complex part. Yeah, but it's complex, but you can get there. You know, like already, talking about the last question, like, what's the most complex part? I think that it's a matter of working. If you can work with CADs, it can handle that. But you can have to understand. When it's up to get to the dies, it gets more challenging. That's why those gears are more challenging. But this is a kind of complex part, and you can already use the simulation for talking to any software you want. Okay. And when I talk about any software you want, you can talk also with sensors. So let's say you have a software, you want to get key form simulation, like preparing results with your software. So your software, let's say another software, it creates, it says, okay, I want this. And you send some ideas and it do the simulation needed. You can maybe you should not even open key form, just analyzing it, and then key form do some analysis and get it back to you. Why I'm saying this? Because the same idea is, let's say you did a simulation and okay, and have a result. I said, okay, it goes to the process, okay? Good results, and this is gonna be implemented. However, in your press or your mill, rolling mill, you are like measuring temperature, velocity, you're measuring, you know, thickness, dimensions, and you are getting all of this and bringing back, to your system. And you're gonna say, okay, you're gonna say, opa, well, you're gonna say like, well, I am considering the temperature, let's say in the second operation, I am considering a temperature like 1100 Celsius. However, I am measuring in my press that the temperature is actually 900 Celsius. And I say, that's a problem because my mold is not appropriate and the dimensions are not very good. But you are reading that, you read this and inform to your software that is doing something different, and you correct it in real time, let's say in real time, and then you can, you know, find better results and change some variables to now stop considering what you were considering before because you thought that was the temperature, and now start considering the real temperature. It's just an example. So I understand by real time, of course, for simulation, we have some time to simulate, but we are already get to some point, to a certain point, that we are already working and talking and put everything together, and also learning, and also using, you know, artificial intelligence to help us working on this. And this is one point. So what I would say is that you can predict, you can give solution, but you can also optimize. And we're talking about, when you talk about this real time, I'm looking to this direction. If I hope I answered that, I'll answer your question very well. And if no, please let me know.
Thank you, Dr. Alisson. Bueno, creo que con esto damos por concluido esta videoconferencia y agradecemos al doctor Alisson Duarte por tan interesante conferencia y pues agradecemos su asistencia y participación de todos ustedes y les deseamos salud a ustedes y a sus seres queridos y les recordamos que el capítulo estudiantil Material Advantage tiene presencia en Facebook e Instagram para que puedan estar enterados de los próximos eventos que se llevarán a cabo y pues muchas gracias por su atención y hasta luego. Thank you, Dr. Alisson. Goodbye.
Thank you all.